So SQL is a very useful tool for anybody who works with data, and that includes us geospatial professionals. So SQL, or Structured Query Language, allows you to create databases, manipulate databases, and query and work with tables inside of databases. So in this video, I'm going to provide an introduction to SQL and how we could use it to query our data using the tabulated or aspatial attributes, and also based on spatial relationships. So before we get started, I just want to introduce the environment. So I'm working inside of QGIS here, so open source free GIS software, and I'm specifically working inside of this dbManager, which is a plugin that natively installs with QGIS, allows you to work with databases. And we're going to work with some data for the US, which is stored inside of this US data geo package, which is like a file geo database, and you can see all the layers listed there. So there's more functionality with databases if you use a more robust system like PostGIS, PostgreSQL, which is a true client server setup. However, we are not. However, I didn't want to set up all that for this demonstration, so I'm just simply working a file geo database, which does have some limitations, but it generally works okay. And also, if you want to work inside of like a PostGIS or PostgreSQL database, the commands are going to be really similar to this. Okay, so first off, let's look at just doing some basic selections. So to start a selection, you want to do select keyword, and note that in SQL it's not case sensitive, so the keywords don't have to be all uppercase, but that's generally considered the standard way to do it. So I'm going to try to do that throughout. So I'm going to do select asterisk, which indicates or means all the columns or fields, from another keyword, and this tells you which table you want to relate to or select from. So I'm going to do this county summary table, and then generally it's considered a good practice to end your statement with a semicolon. And we'll do execute. Okay, and that returns a table. You can see it's got all the record or all the attributes for all the records, and we also have this geometry column here, which is the geometric information. And there's 3,108 records, and that's basically all the counties in the country. So we really didn't do any querying here. We just simply returned the entire set of data because we haven't actually limited the selection. So to expand this, it's generally you want to include a where statement, which allows you to actually query the data or subset it based on some criteria. So I'm going to add to this where elevation median is greater than 1200. And also, I don't want to get back all the columns now, so I'm going to do a subset of the columns. Specifically, we're going to kick back the name column and the elevation median column. So what's going on here, or what's different from what we did in the prior example? So now, instead of just selecting all the records from the table, we're only going to return the ones that meet this criteria. So this where clause is used to do your subset or your query. And now, instead of returning all the columns, I'm just going to return a subset of the columns as named there. Okay, so I'm going to run that, and let's see what we get back. Okay, so now we have less records. We have 265 records as opposed to the 3,000 and some odd records. So these are the only counties that actually met our query criteria in this case. So this is the value or use of the where clause. One thing that's nice about SQL is it's generally pretty readable. So for example, here you could just read this as select these columns from this table where elevation is greater than 1200. Oops. There's other ways to do. So there's other ways to limit your query. So in this example, I'm just adding in a limit, and I'm going to set that to 10. So what that means is it's only going to return 10 records. That's, if you're a coder, this is kind of similar to doing like a head or a tail argument, where you're just spitting back the first X number of records or last X number of records just to get a sense of the query results. So here we're just limiting it to the first 10. Okay, another common technique you'll see in SQL is the use of as. So as is used to provide or change the name in the table. So you give it like an alias name. So in this example, what I'm doing is I'm assigning new names to these fields that will show up in the attribute table. So we want the name field, but we're going to call it county because it's the county name. And we want the elevation median, but we want to call it just elevation in this case. And everything else is the same. We're still going to select from the county summary table. We've got our same where clause, and I'm just going to get rid of the limit here. And then semicolon to end the statement. Okay, so now you can see that the column names have changed. So instead of having the original names, we now have our new names, which I realized I spelled wrong. Just run that again. So anyway, so that's our so that's just changing the name. So that can make your output a little bit more readable. For queries, there's a variety of different operators, and they're actually pretty standard operators that you would use in other like coding languages or querying methods. So we've got equal, greater than, less than, greater than or equal to, less than or equal to, and not equal to. And those are the operators that you would use. So they would go, basically here in the clause. So for example, if I swap this out for less than, then we're going to get back all the counties that have a median elevation less than 1,200 meters. So that's pretty standard. If you have multiple criteria, you can combine them with these Boolean operators. So we have and, or not. So for and, basically that means it's going to return only the criteria that meet both of the criteria. Or would be one, it meets criteria A or criteria B or both criteria A and B, and not meets A but not B. The one that's kind of missing here is XOR, which is basically A or B but not A and B, which can be developed using combinations, but I don't believe there's actually like an XOR operator. Okay, so let's add something to this to expand this out. So we're going to now return all the counties that have a median elevation greater than 1,200 or we'll do less than 300. So actually, I need to swap this back to greater than, since those are mutually exclusive. All right, so there's our OR operator. So basically, the high elevation counties and the low elevation counties should be returned, but not the ones in the middle. Okay, and there we go. That's our set. Note if I did switch this out to less than, well, I guess that wouldn't work. We'd want to do greater than 1,200, and then we'll just do an and here instead. So it has to be greater than 1,200 and less than 300. So if we run that, we get back none because those two things are mutually exclusive. So no county is going to have meet both of those criteria. Okay, so let's look at some other selection options. So this between keyword can be used to select values based on whether they occur between two end members. So all we're doing here then is swapping this out. So I'm going to drop this, and we'll say where the elevation median is between 1,000 and again, that's another keyword, 2,000. Okay, so what that's going to kick back is just the counties with the median elevation in that range or between those two end members. And those are your option, and those are the results there. So that's another way to do a selection. N can be used to determine whether or find features that are within a list of options. This is used a lot for like categorical data or like unique values. I'm just going to dump this in. I have the code over here just to save some time. So basically we're switching tables now. So instead of working in the counties table, we're now working in this geology table. So to read this, it's basically select all the columns from the geology table where the major one column has one of these two values. So effectively we're selecting all the units that are either limestone or dullstone in this case. So let's execute that. This takes a little bit longer because the table's a bit bigger. So you can see there's a lot of records there. So there's 45,000 records were returned that met that query. So it's a pretty big data set. Okay, you can also do not in. I'm not going to demonstrate that, but not in is just kind of the opposite or the inverse. So you're going to return all the records that are not limestone or dullstone. So just kind of switches it. To try to make this even a little bit more generalized, you have the like keyword, and this allows you to search for features that have a string that meets a criteria. So this can get kind of complicated, but I just, again, we're just kind of introducing it here. So I'm going to dump in an example, and then we'll talk through it. Okay, so select all the fields from the geology where major one like, and then we have this % stone. So basically percent, it means that this represents missing characters. So it could be no characters, it could be one, or it could be multiple characters. So effectively what we're saying here is find all of the geologic layers where its type, which is this major one field, ends in stone. So basically any unit that ends in stone will be returned. So let's hit execute there. And again, this might take a second because, again, it's a pretty big table. Okay, so if we look at the type, the major one field here, we've got dullstones, mudstone, limestone, sandstone, probably there's a couple other there, but effectively anything that ended in stone. So this percent thing is known as a wild card, and it just denotes in this case that the stone is going to be the end of the sequence as opposed to in the middle or the end. You can also use an underscore, which means just one missing character. And if you have special characters that have special meaning in SQL, then you can use the backslash as an escape character. So this is just, again, a brief introduction to this. There's a lot more you could do with this in terms of query. Again, you can think of it as a generalized, more generalized version of the in operator. So instead of it being that specific string, you can look for a string that contains a certain series of text, for example. Okay, so it's also common when you do data queries that you would want to summarize the data in some way. So SQL has a bunch of built-in data summarization operations. So returning the minimum, the maximum, the counter number, the average, the sum. So I'm just going to run one of these just so you can see what that looks like. And honestly, this is generally more useful when you're doing grouping, which we'll look at later. Okay, so in this example, we have select name as county. There's an example where I kind of screwed up the keyword. Again, it would accept that, but the standard is the uppercase. So select name, but call it county, and then return the max median elevation as elevation from county summary. So let's do an execute here. So what we got back in this case was not all the records, but just the record that had the maximum elevation. So this San Juan County had the highest recorded median elevation, 3,458 meters. So we're just returning the max again as opposed to all the median elevations. And we'll see that again when we look at grouping. All right, you can also change the order at which your results are delivered. And that can be based on one field or could actually be based on multiple fields. Okay, so let's look at an example of that. So dump this in here. So this is another example. So basically I'm selecting the name field, calling it counties, the elevation median field, calling it elevation, and the median temperature field, and calling it temp from the county summary. And again, probably it'd be better to capitalize that. And we're going to order by elevation in a descending order. So the highest elevation at the top, and then temperature in ascending order. So the lowest temperature at the top. So you're just effectively changing the order based on the values. And then let's run that. There we go. So that's our highest elevation, low in the lower temperature. So this is increasing as you go down, and this is decreasing as you go down the table. So effectively it's changing the order. So this keyword means descending order. This keyword means ascending order. Note that this also works for text or characters. In this case, instead of it being increasing or decreasing value, it's going to be alphabetical order, right? So A to Z, Z to A. All right, so this is kind of a specific case, their example. So if you want to return something different in a new column, depending on the results or query relative to another column, that can be accomplished with case. If you're a coder, this is kind of similar to like an if-else statement. So if this is true, do this. If else, do this. And then else, do this. All right. So this is an example of that. So I'm going to dump in this and we'll just talk through it. All right, cool. So we have select, name is county. So we're going to return the counties again. The median elevation is elevation. And then here's our case statement. So when the elevation, the median elevation is less than 1,000, return low elevation. When it's between this range, 1,000 and 2,000, return medium elevation, and then anything else return high elevation. Note that for else we don't have to have like you don't have to include a query there because it's just the default. And that ends the statement. That's the case statement, and then we're going to call that output elevation class, which will be a new column in the output table. We're doing the selection from the county summary table. Note here, I use that up here so we know that it's coming from that table. Probably would work without it though. And then we'll sort descending. Okay, so what we get here then is a return column where we have high elevation, all the high elevations. This may be slow because it's big, and then mediums, lows. So sorting descending. So effectively you're creating a new field and you're populating it with some text, and what gets populated in there depends on the elevation stored in this other field. So that's a case statement. I think I'm just, this is just a quick slide on null values. So you can query and find where there's missing data using isNull, and you can also query to find where there is not missing data using isNotNull. I'm going to skip over that, but there are some examples here if you'd want to look at it. Okay, so now we're going to look at grouping. So you, instead of getting a record by record result, you may want to group the records in some way and return a grouped output. Okay, so let's look at an example of that. Okay, so I'm going to pull in another example here, and then we'll read through it and see if we understand the syntax. So we want to select the unit age, but we're going to call it age, and we're going to count the number of units based on the unique name. So the number of unique names will be counted per unit, and then we'll call that unit count. This is coming from a table called carbonates, which is a layer that it has all the different carbonate rocks in the country. And we're going to group it by age, which is the geologic is the unit age, and then we're going to order it descending. So we're going to get back the geologic age that has the largest count of unique carbonate formations at the top. So let's execute that and see what we get. Oops. Oh, I had it selected. It just tried to run the selected part, which didn't make any sense. Okay, so what do we get here? So the ages were basically like the periods, different well, it's not really periods, it's different geologic periods. You can see there's a bunch of them here. And then we get this unique count field, and what that is it's counting the number of unique formation names within that age group. So in this case, there were, according to this table, 8,855 uniquely named formations that were carbonate formations and that occurred in the Ordovician period. And then if we go down to, let's see here, let's pick one of these. Some of these are pretty specific. This late Jurassic to late Cretaceous, there were actually only 2 formations that were found or delineated in that age range. So generally your group by field is going to be something that represents categories. So it's generally categorical or ordinal or something. And generally what you're summarizing is going to be, if it's using something like min or max or average, is going to be something continuous, but you could use count for something categorical. So that's an example of doing a grouping. And again, you're generally going to provide the summary statistics with that. Okay, so let's look at an example of halving. So once you group data, you can't really use a where clause because that kind of becomes ambiguous. So if you want to do a subset of the groups, then instead of using where, you're going to replace that with halving. So basically halving is just where, but for groups. So let's pull in that. Or pull an example for that. Find one here. Here we go. So I'm going to pull in this example, and we'll look at it. So this is the same thing we did before. So we're basically counting the number of uniquely named carbonate formations per age group. But I've added in this halving, and I've set unit count greater than 1,500. So what that means is it's only going to return the ages that had more than 1,500 differently named carbonate formations within the age group. And then we're sorting descending, so we get the highest one at the top. So now we only have 14 records, and these are our geologic ages that had more than 1,500 differently named carbonate groups. So that's halving. So again, it's basically where, but for group data. Okay. Now we're going to look at joins. So databases commonly can store multiple tables. And one of the great powers of working in this data structure is that you're able to actually relate those tables. So if you're going to relate tables, you have to do it using some type of unique identifier. So like basically a shared or common field. So I'm going to demonstrate how to do that. And there's a couple of different types of join operations. So an inner join just maintains records occurring in both based on the common field. Left is all the records in the first table and only the matching records in the right table or second table. Right is just the opposite. So you only get back the records in table 1 that have a match in table 2. And then full maintains all the records from both tables. Okay, so here is an example using an inner join. So only records in both tables are returned, or that occur in both tables, or have a match in both tables. Okay, so here's the syntax for this. So we're selecting the county, the county name is county name, and the state name is state name from the county summary table, and we're given the table now an alias of county. So you can assign aliases not just to the column names, but also the table names themselves. And then here we're defining we want to do an inner join. Note if you put just join, the default I believe is inner, so it'll just assume it's an inner join. So we're going to join to it the states FIPS table, which is basically just a list of state names and state FIPS codes, and we're going to give that the alias ST. And then how does it know which ones are related? Basically, we're telling it that in the county table, the state FIPS is equivalent to the FIPS code in the state table. So effectively, it's just matching them up based on the common FIPS code, which is sort of Federal Information Processing Standard, something like that. So it's a unique identifier for each state. Okay, so let's run that and see what we get. So the county name and then the associated state that it's in. So I'm just really quickly, I'm going to show you the original data just so this makes sense. So we'll just select, we'll just do everything from county summary. Oops. Select everything from county summary and return that. So this is all the county level data. Note that this is the state FIPS code there, but there actually is no county name. State name. There's just the county name. If we look at the other table, state FIPS, basically it's just the FIPS codes, the postal codes, and the name. So we're basically using this common FIPS code column from the county level data and the state level data to add this county name or state name to each county. That's the idea. All right, here's an example of another join. So I'm going to dump this in and then we'll talk through it. Okay, so let's hit execute here. Well, first off, let's talk through it. So we're going to select the state name, and we're going to return the average median elevation by county, in this case per state, because we're doing the grouping, as elevation. This is going to be from the county summary table. We're going to join it to the states table, again, so we can get the state name. And then once this is, again, is the primary foreign key relationship. And then this group by, what that's doing is it's saying group them by state name, and we are only returning ones that have an elevation greater than 1,000. So in summary, basically what we're doing here is we're returning a result that's going to be every state where the median elevation for all the counties in the state are greater than 1,000. So this is a good summary of some stuff we've already talked about. So here, for example, we're using having because it's been grouped. We are doing an inner join based on the common FIPS code. We're using a bunch of aliases, and then we're also using this average operator to return the average or mean by county, since we're grouped by county. So let's run this. Okay, so there we go. So there is our list. So there are 8 states. So these are the 8 states that had a median county elevation greater than 1,000. All right. This section of the background talks about database manipulation. So like adding or creating and deleting databases, creating, deleting, or manipulating or changing tables, or manipulating or adding or removing individual records. I'm going to cover any of that in here, but that's what this section goes through. Okay, so this last section is just some examples of now doing spatial queries. So you may notice that we really didn't do any queries initially that were they relied on any spatial information or spatial relationships. So everything we've done up to now could have just been done with attribute tables, with just ignoring the geospatial information. So my goal here is to show you how to actually do some queries that use spatial relationships. And this would only work in a database that's basically spatially enabled or has these operations available. Okay, this is some backgrounds on geometry types. Okay, so let's look at this example. So this ST grid will return. Well, actually, that's spelled wrong. This should be StSrid. That's going to return the EPSG code for a layer. And actually, it'll do it feature by feature. So I'm just going to have it do it for the first record here. So we're basically saying select the geometric information from this table, and we're just going to return the first record. So that's the code. So that's the EPSG, or European Petroleum Survey Group, code for this projection information, which I believe is like Albers equal area. I'm not sure. So effectively, this StSRID returns the projection or spatial reference information. If you remove this limit, it's actually going to do it for every feature, I believe, in the table. So they all have the same reference, so you'll just get that repeated the number of times, the number of times equivalent to the record number of records in the table. So that's what this does. There's also StTransform, which I'm not going to demonstrate, but that can be used to perform a projection transformation on some data. Okay, if you want to have a look at the geometry information, then you can use this StAsText method. So here we're saying StAsText geom from county summary. And we'll execute that. And what we get back is the geometric information for each of the counties. So effectively, these are all the points that make up the polygons that define the extent of the county within the spatial reference. This StAsText returns it as what's known as a well-known text, which is kind of human readable. If you don't wrap it in that, then you're going to get back this, I think it's hexadecimal, I'm not really sure, but it's obviously something that's not human readable. So that StAsText provides human readable output. Sorry, I missed this. And then some other operations, you can return the geometry type. So point, line, polygon, multi-point, multi-line, multi-polygon, geometric collection, for example, for geopackages. And then STX, STY can be used to return the X and Y coordinates relative to the projection for point data. Okay, there's also a bunch of operations for returning some geometric information or calculations for features. So here's an example of that. Let's move this one to the next slide here. Okay, so we're selecting the name as county, and we're going to return the area for each county, and we're converting it into hectares because it's going to be in the map units, which in this case is square meters. So this ST area, that's what it does, is it calculates the area, and we're doing that from the geometry field. So we're specifically saying calculate the area from the geometry field that's stored in this table, then divided by 1,000 to get into hectares as opposed to square meters. And then we're just going to order them descending, so it's going to have the largest area at the top, and then it's just going to return 1. So effectively what we're doing here is we're getting back the land area in hectares for the county in the country with the largest land area. Oops. Oh, then I had it highlighted again. Okay, there we go. So this Elko County that had that land area. Okay, so key thing here is ST area, basically calculates area for polygons, and you have to feed it the geometry information from the table. So if you don't have any geometry information in the table, you can't actually, calculate it. Okay, so for lines, you can calculate the length. So let's run one of those. All right, so we have select the sum or the total for StLength of primary roads, geom, divide by 1,000, total kilometers, and then from primary roads. So what's going on here is I have a table of all the primary roads in the country, and I'm trying to return back the total length of all those roads. So StLength returns the length, and that's going to be relative to the map units. So it's going to be meters. We divide by 1,000 to get it into kilometers. And instead of getting a measurement for each individual road segment, we're summing them up so we get a grand total length. I'm not going to run this because this takes a while, so I don't want to have to, wait. So anyway, you'll just get back one record and it'll be the total length, but we're just not going to run it to save time. Okay, also as a quick note, if you're calculating, you're not supposed to use the length on polygons. So if you want to get the length or like the perimeter of a polygon, there's actually like an ST perimeter function. Okay, so you can also get the centroids for polygons using StCentroids. So let's have a look at that. So again, we're going to spit back text, well-known text. And now instead of getting the geometry information, we're going to condense that down into a centroid. So you're going to get a coordinate pair for each polygon as opposed to all the vectors. We're going to call that centroid, and we're only going to get the results for counties that have a state FIPS code of 54, and that happens to be the FIPS code for West Virginia. Okay, so there we get back our coordinate pair, and again, that's all the centroids for West Virginia. Okay, let's skip that. StWithin. So then now we're getting into examples that rely on spatial relationships. So we're going to start off here with StWithin. Okay, let's dump this in here. So we're going to select the name as airport and the airport identifier as ID from the airports table, which is effectively a point layer of a bunch of airports. And we're just going to call that table A. And also from the county, we're going to use the county summary table, and we're going to call that C. And we're going to return airports that intersect or are within the counties, and then we're going to look at only a specific county that has this geo ID 42003. So this happens to be the FIPS code, or also the geo ID for Allegheny County, Pennsylvania, where like Pittsburgh is. So the goal here is effectively to return a list of all of the named airports and their identifiers for just the airports that occur in the Pittsburgh area. Okay, there we go. So these are all the airports that are listed in that county. And again, this is a pretty large data set, just like, tiny airports, not just our other ones. So like, let me pull this out here. There should be like the Pittsburgh International Airport and everything should be in here, but there's like a county airport there, some like landing pads for hospitals. So again, it's a pretty large data set. Okay, so anyway, that's an example of StWithin. So finding all the points that fall within polygon, but here we're specifically looking for a specific polygon, in this case, specific county. Note that this StWithin is actually within a where clause. So you're using it to do a query, but instead of it being a table query, it's now a spatial query. Okay, StContains. It's kind of the opposite, so I'm gonna dump this in here. Have a look at it. Okay, so let's look at this one. So now we're doing contains as opposed to within. So we're going to grab the name field from the counties table, and then we're going to count the number of unique values. So in this case, it's a unique ID for each airport. So effectively, we're counting the number of airports. From this West Virginia PA data set, which is just the counties in West Virginia and PA, we're going to call that table C. And then the West Virginia PA Air as A, which is all the airport points in West Virginia and Pennsylvania counties. And StContains, so the county geometry and the airport geometry, we're going to group by county, and then we're going to order it descending. So effectively what we're going to do here is count the number of airports per county in West Virginia and Pennsylvania, and then sort that result descending so the county with the largest number of records occur at the top. Note that StContains, we're really querying here the counties relative to the airports as opposed to the airports relative to the county. So it's counties that contain the airports as opposed to points that are within the counties. So that's kind of the difference between StWithin and StContains. Okay, so let's run that. I don't think this takes too long. Okay, there we go. So we have Buck County, there's the largest with 37 records. And then down here at the bottom, we have Work County, West Virginia with one mapped feature. So lots of things going on there. We got our group by, we're ordering descending, we're using a spatial query, we're using a lot of alias names, and we're doing a count summary. Okay, StIntersex and an intersection. So let's dump that in. Copy. Okay, so this looks kind of complicated. So I'm going to explain basically what's going on here. So what I want to do is I want to count the length of roads on a county by county basis within West Virginia and Pennsylvania. So here's how I accomplish that task. So again, from the tables, I'm selecting the county name, and I'm getting the lengths. So I'm going to sum the length per county. So here's StLength, which we looked at, and sum. But I only want it if it intersects, where I want to intersect the data relative to the counties. So if you have a line that passes through multiple counties, you want to split it, and that's going to get returned as length kilometers. We've got from our from table, which is our roads table, we're joining to it the West Virginia PA as C table, and how are we joining it? We're just joining it using StIntersex, which basically is a spatial intersection, and then we're grouping the result by name. So StIntersex is basically a query result that's going to return yes or no or true or false depending on whether a feature intersects another feature. So that's how we're using it as a join there. And then intersection actually returns back the actual geometric intersection. So that was kind of complicated, but it's not too. I mean, you're doing something fairly complicated in a few lines there. I'm not going to run this one either because I remember it taking a while, so we'll just skip that one. But that's just an example. That's an example. Okay, so if you want to find features that are like within the distance of another feature, all right. So to accomplish that, you can use StDistance. So let's look at an example of that. You'll dump that in, paste. All right, so we got select the airports from airports table, and then we also have roads there where StDistance of the roads are within a certain distance of airports. So let's pull this apart a little bit, make sure we understand what's going on here. So I've got select West Virginia _ PA _ air. So that's all the airport points in West Virginia and Pennsylvania. And we got a dot asterisk. So what that means is select all the columns. And that's coming from this specific table. And then we've got West Virginia PA roads. Note here that we're not actually pulling any fields from that object. So that's why I did the dot asterisk just for this table and not for this table. So we're just getting results back for the airports, not the roads. And then this where we're looking at comparing a distance. So effectively this is going to be a test. So if it's within this defined distance, it returns it. If it's not, then it doesn't return it. Let's run this. I don't remember how long this one took. We'll give it a shot and see. Apparently took a while. While that one's running, I'll just... oh, never mind, it's done. Okay, so there's our records. So these are all of our records that are within a certain distance of all the airports that are within a certain distance of roads, in this case 2 kilometers. I haven't done this yet because I didn't want to eat up a lot of time with it, but real quick I'll just show you. If you want to load a result to the table, you can, or to the map, you can do that. It just has to have a geom field if you're showing it the geometry. If you just want the table, it doesn't have to have that. So if you do a load there, it should dump those points back in to the map. That can be a bit slow. while that's running, I'm just going to mention the last couple options here, or examples. So StBuffer does a buffer, so like a proximity analysis. So this can actually be used very similar to like StDistance, so finding features that are within like a distance of something. So oh, I think this is done. So let's have a look at that. We go into the map here. I think I crashed it. Sometimes this loading can be slow, especially I've ran a bunch of queries here. Okay, so yeah, we'll see if that loads. If not, I'm just going to just discuss these last couple and not actually run them because they take forever. Okay, so what we're doing in this case is I'm selecting the name as county from the county summary table, and I'm calling that table C. And then we have this Preston County object, which is the boundary for Preston County. We're going to call that P. And then we're going to do where StIntersex, StBuffer, geom, 50,000, and then county geometry. So what's going on here? So basically what we're doing is we're trying to select all the counties that are within 50 kilometers of Preston County, West Virginia. And since we do an intersex, the whole extent doesn't need to be within the county, just a part of it, right? So we'll run that just for the sake of completeness. So let's have a look at that. Let's see, did this actually load? Okay, there we go. So there's those airport points that are within a certain distance of interstates or roads, or I guess primary roads. Okay, so let's run this last couple queries here. So select name as county from county summary as C, Preston SP, where StIntersex, this buffer, and then the geometry. So let's run that and have a look. Okay, so there's our list. So these are all the counties that are within a 50 kilometer, at least partially, I guess, within a 50 kilometer buffer of Preston County, West Virginia. Note here there's no geometry fields because we just had to return the name. If we wanted to like map that out, then we'd have to include the geometry. So let's see if we could do that real quick. So we'll do scene name as county, and then we'll also do c.geom to get back the geometry. And that should work. So let's do an execute on that. So we get the same result. We just have the geometry column now. And let's see here. Oops. Let's see. Oh, this needs to be after, right? Because I signed the wrong alias. So we'll do a cut there, and we'll paste it after the as, and execute. Oh, sorry. Gotta remove the comma here, and then move the comma to after the alias name. Okay, that should do it. Okay, so now we have the county name and then the geometry information there. And we'll click on load here. Let it load to the map. Oh, there they go. So those are so if you're not familiar with this area, that's Preston County right there. And then these are all the counties that are within a certain distance of that feature. In this case, 50 kilometers. So at least a portion of each of these counties are within 50 kilometers of Preston County. Okay, and then our last example here is StTouches. So let's run that, and then we'll also look at the output. So go back in here to our dbManager, dump in this query. Okay, so we have select CNAME as county from county summary, and then we're going to call that C. And then we're also using this Preston as P, which is just a table that has just Preston County in it as a polygon. And then we'll do where ST touches the Preston County geometry. So the idea here is it's going to return only the counties that touch Preston County, or in this case, share a boundary with it. So let's execute that. Okay, so those are all the counties that border Preston County, West Virginia. And then let's just plot it to finish up. So we'll do CNAME as county, and we need to add in here the geometry. So we're going to do c.geom and execute. Oh, what did I do? Oh, I forgot. I got to put the comma in, right, to separate the list of fields. Okay, there we go. So there's the geometry information, and let's load that to the map. And we'll minimize the dbManager there, and turn this off. So there's all the counties that touch or border Preston County, West Virginia, as you can see. All right, cool. So that's an example of queries. Note there's a bunch more you can do. In this slide, I listed some other examples of useful functions and methods and whatnot. If you are interested in learning more SQL, I would highly recommend looking at the W3 Schools SQL page. It's pretty awesome. It's pretty easy to follow. I think the easiest way to learn is just get some data that you're familiar with, and then try to run some queries on it, and build up from there.